And so we are off with our 10th online training session. And in this one, I'll show you how I would have taken on the second part of our FlowNext training network. And I do want to say, this program has an experience restriction of not solving it yourself. So, if you've not struggled with the exercise on your own, then you may not watch the rest. Is that a deal? All right. Let's quickly look at the system again. We have hydrogen that is cooling our generator, and we need to achieve equal flows through the generator cooling lines with 50 kilowatts of heat load and 10 kPa pressure loss at a total system flow of 0.18 kilograms per second. The water side will in turn take up the heat from our hydrogen and release it into our beautiful pond with all sorts of tropical fish in it, or something like that. Okay, let me create some space here and then drag in the pipe that connects the heat exchanger with the reservoir. Specify a length of 8 meters, diameter of 3 inches and roughness of 60 microns, and add secondary losses for the bend and also the outlet into the tank, giving me a total K value of 1.216. As explained earlier, for system level modeling, I personally choose to rather make use of the secondary losses on the pipe to account for bends and junctions than using the components itself, which uses directional Reynolds number dependent lookup tables for convergence and take up a lot of working space on my canvas. For the exit loss to the tank, an axial restrictor with discharge component might have been a more visible choice, but I wanted to show you guys the actual loss value of 1. So let's keep it as it is for now. And then I'll add 3 increments to discretize the pipe. Next, I'll add the reservoir with a chosen volume of 3 cubes and diameter of 1. You could have selected anything sensible here, since it wasn't specified. I have to move the boundary values, but since the pressure on the tank is part of the problem specification, I'll change the boundary value option to pressure and specify a value of 1000. But I still want to stick to some kind of mass flow specification since the system mass flow was also specified. So I'll change my inlet boundary value to mass source and specify a value of positive 0.18 and solve to see if everything is in order before I go too far. Now I'm going to continue with the rest of the system, but keep the pressure boundary value specified on my reservoir. As we discussed in session 3, a pressure boundary in the middle of my network will isolate the sections on either side, which will analytically be similar to having 2 separate sections. And if my mass flows on both sides are not exactly the same, a mass source will be created on that position, which will lead to a further change in temperature. For our case, we know that the system pressure needs to be controlled from our reservoir, so we need the pressure specification on this point, and will therefore employ it with the appropriate level of caution and due diligence. Let's proceed with our 2-meter pipe section. Here I need to add the losses caused by the abrupt inlet from the tank to the pipe, giving a value of 0.5. And also the losses on the junction through flow section. Now, as you can see, this through flow loss is basically negligible, so I don't normally bother to include this in my models. Anyway, add 3 increments and then a boundary value, on which I will specify a mass source to stick to the exact system mass flow. Now normally having 2 mass source boundary values at the ends of my network will be a disaster. But since I have the pressure boundary value in the middle that separates the flow on both sides as discussed earlier, it makes perfectly good sense in this case. Let's solve it to see if Flownex is happy. It solves just fine, but I can see that there is something that Flownex needs to tell me. So let's look firstly at that. Flownex points me to the reservoir and say that the node is an internal fixed pressure node and temperature is not fixed. If mass source is drawn from the outside, the temperature of this flow will be assumed to be equal to the ambient temperature, which is 15 degrees C by default, by the way. This warning is therefore only for informative purposes and points at the risk of having a pressure boundary value in the middle of my network. And just to check that I'm still enforcing mass flow balance on my system, I can check the mass source result on my reservoir. And 2 to the power minus 17, I'm still in balance. Next up, I'll model the first of my 2 cooling lines with the required inputs. And select a bend and a junction through flow loss to be consistent for this training's purposes. And again increments. But I'll take the liberty of modeling my orifice or valve as well to enable splitting of my mass flows. For such a case where I don't have any information on the type of flow controlling component, I personally like to use the restrictor with loss coefficient due to its generalized inputs. I'll assign the same diameter as that of the pipe with a temporary contraction coefficient of 1 and a rule of thumb orifice loss of 0.65. Get my boundary values in place and specify the equal parting of the total flow. Solve the model. And just confirm that there are no new warnings issued. Now, let's add the 2 10-meter sections. Move the boundary values and solve. Still perfectly under control. Due to the lack of information on my generator's heat removal section, I'll just take a flow resistance component, move my boundary value, and take a first guessed admittance value of 1. Let's see what pressure drop we get. To the power minus 5. Let's get this onto my canvas. So I can increase the resistance by 1,000,000, or in terms of admittance, decrease by 1,000,000. That looks good. Now let's add the 50 kilowatt heat load and solve again. You'll notice a small change in pressure drop, and that's because of the change in density with the change in temperature. But still, close enough for now. Let's copy this to the other side and get another pressure drop result displayed for this section. And solve. Let's add the rest of the cooling section. something here that will be of good use. If I want to align my icons in any way, I can go to Layout and select the display correction that I would like. That keeps it neat and tidy. Add my combined boundary mass source and solve. So now I can see that there's still a difference in pressure loss over my generator section, and that is due to the difference in mass flows between the two pipelines. So let's get the mass flow result under I. And since this will be a pressure loss component that I still need to design, it makes a good place to use my fixed mass flow functionality. This helps me to temporarily have the ease of mind that Flownex will help me to maintain equal mass flow distributions each time, no matter what the system's layout. Remember that Flownex will ignore the component's characteristics and input values once I selected the fixed mass flow option, and calculate the required pressure drop or pressure rise over that component that will allow the specified mass flow through the system. Furthermore, the rule with a fixed mass flow specification is that I cannot use a mass source boundary together with my fixed mass flow specification. But in our case, I have two lines, so I still have 1 degree of freedom for calculation purposes, and therefore I'm not overspecifying my network. With equal mass flows ensured, I can go ahead and use the designer to correct my admittance values for a perfect pressure loss of 10. And I can add both of them since they are independent of each other due to my fixed mass flow assistance. Let's run it and see what we get. Perfect. Now, with my generator section calibrated, I can go ahead and calculate the orifice or valve opening required to divide my flow equally. Got it! And it shows an opening area ratio of around 0.54. Let's move on to my long pipe section. And solve it. And all is still in order. Next up is my fan or compressor. Now, I don't have any information on its performance, and furthermore, the problem specification doesn't require me to design such a component, but only enforce the correct mass flow through it. So, I can again make use of the fixed mass flow specification and leave the pressure rise calculations to Flownex. And now, I can complete my network to form a closed thermohydraulic system. I can remove these boundary values, but for a closed loop, there always needs to be a pressure boundary value somewhere to tell Flownex at what pressure the system operates. The temperatures will automatically follow from the heat exchanger's performance, although it might be a good idea to keep a temperature boundary value somewhere in my system for safety and monitor the heat source result on it. For now, I trust that my system is close to its operating point, so I'll skip that process. And let's solve it. The heat exchanger's inlet temperature now proves to be 79.66, resulting from the 100 kilowatt heat load and mass flow of 0.18. And due to this small change in temperature, my pressure losses are a little bit off. So I'm just going to run my designers again and get those values back to where they should be. For the generator section, I'll just install my trusted valve operator and calibrate my generator losses at the design flow. And finally, I can finish this off by obtaining the actual flow area ratio required for a perfect match of flows. Spot on. And for interest's sake, if I were to design some kind of fan or compressor, I would need a pressure rise of approximately 36 kPa at my design flow. This was a mouthful, but I hope you followed and understood each step I took in completing this part of the model. And again, there are many different roads that you can take to get to the same results, so feel free to do it your way. But I hope that you've learned an awful lot in this session. In the next session, we'll look at Flonex's Excel component. Now, this is an extremely powerful tool in the hands of any engineer, so be sure not to miss that one. But until then, be blessed.